Sometimes we get equations in which multiple powers of our variable appear. And when those powers are all positive integers, that's a polynomial. It turns out when we have an expression in which multiple rational powers of our variable appear, that's not a polynomial, but we can pretend it's a polynomial. And pretend we have a polynomial is going to be a very common move that we make as we go on to solve more and more complicated sorts of equations. So each of these expressions, one power of x, another power of x, a constant, one power of x, another power of x, yet a third power of x, one power of x, another power of x, a constant. Each of these expressions has the form of a polynomial, except that the exponents are not positive integers. This last one, it isn't immediately obvious that it has the form of a polynomial, but we can write the square root of x instead as x to the power 1/2. And now we have one power of x, another power of x, a constant. And the key idea here is equations like these can be solved almost exactly as if they were polynomial equations. And in particular, if the polynomial equation in question could be solved by factoring. So can these. It's just that at the last step, where in a polynomial equation we would have x equals a number, in these equations we'll have something like x to the 1/3 equals a number, x to the -1 equals a number. So we'll have some cleanup steps to do after the polynomial solving step. So let's see how this plays out. If we want to think of these as polynomials, we need to be able to think in terms of integer powers. But in this first example, we notice that 2/3 is 2 times a third. And so we can write this expression as x to the 1/3 squared minus 3x to the 1/3 minus 4 equals 0. So this actually works just exactly the way that it did when we were factoring trinomials of degree 4 or 6 by pretending that they were quadratic. We can also pretend that this polynomial is quadratic. And we can say, okay, I'm going to use the AC method. Leading coefficient is 1, so I can use the shortcut. My variable is named x to the 1/3 for the moment. I want two numbers that multiply to -4, so I'm going to have a negative number and a positive number. I want them to add up to -3, so I'll have -4 and 1. One of my factors has to be 0. Either x to the 1/3 is positive 4, and we have 4 minus 4 equals 0. Or x to the 1/3 is -1, and we have -1 plus 1 equals 0. If this were actually a polynomial, I would be done right now. But this isn't actually a polynomial. Instead of just having x by itself, I have x to the 1/3. Now 1 and 3 are both odd numbers, so I don't need to worry about signs. I can say that x is 4 to the power 3 over 1, or just 4 to the power 3. So x equals 64 is one of my solutions. I can say x equals negative 1 to the power 3 over 1. So x equals negative 1 is my other solution. X equals 64, x equals negative 1 are my two solutions. And you can confirm that these really work by plugging those in on the calculator. Okay, this next equation, I have x to the 5/3 minus x to the 2/3 minus 20x to the negative 1/3 equals 0. Now, if this were a polynomial, I would notice that I have an x in every term and say, I would like to factor out the smallest power of x as a common factor. And I'm going to do that here. Of these three powers of x, negative 1/3 is the smallest. So I'm going to factor out x to the negative 1/3. When I do that, I'm going to subtract negative 1/3 from each exponent. So I've got x to the 5/3 minus negative 1/3 minus x to the 2/3 minus negative 1/3 minus 20x to the negative 1/3 minus negative 1/3 equals 0. X to the negative 1/3 times, well, this works out to just x squared. This works out to just x to the first power. And this works out to just 20, as long as x is not 0. I'm not sure about this if x is 0, but we'll think about that in a minute. Right? X to the 0 is not 1 if x is 0, but we'll worry about that in just a minute. X squared minus x minus 20, I know how to factor that. I can use the shortcut. I want two numbers that multiply to negative 20 and add up to negative 1. That's going to be negative 5 and 4. So one of these factors has to be 0. X to the negative 1/3 is 0. X minus 5 will give me x equals 5. X plus 4 will give me x equals negative 4. Okay, and now I need to look at all of these numbers and see if these make sense. Can x to the negative 1/3 be 0? Well, I have a negative exponent here. So this represents 1 over the cube root of x. Can 1 over something ever be 0? No, that can't happen. What about this 5 and negative 4? Well, the only concern I have is the original equation defined when x is 5 and when x is negative 4? And yeah, because this is an odd denominator, every term of the expression is defined when x is 5. Every term is defined when x is negative 4. Now, because it seems weird that we've got these nice integer solutions when each of these expressions is going to work out to a really nasty decimal, I might actually sit down with my calculator and say, if I take 5 to the 5/3 minus 5 to the 2/3 minus 20 times 5 to the negative 1/3, do I really get 0? And I find that I do. If I take negative 4 to the 5/3 minus -4 to the 2/3 minus 20 times -4 to the -1/3. Do I really get 0? Yeah, in both cases. I really do get 0 if I just throw all of that into the calculator. So it's actually fine. 5 and -4 really are the solutions to that equation. Okay, let's see a couple more examples. Here we have negative integer exponents. 2 times x to the -2 minus 7 times x to the -1 equals -15. But of course, -2 is -1 times 2. So this is 2 times x to the -1 squared minus 7 times x to the -1 minus 15 equals 0. So again, we can factor this as if it were a quadratic, where our variable is just called x to the -1. Here, my leading coefficient is not 1, so I need to use the full AC method. I'll set up a rectangle with 2 rows and 2 columns. I'll have AC is -30, right? 2 times -15. B is -7. And I think the two numbers we want are -10 and +3. So I'll have 2 times x to the -1 squared minus 10 times x to the -1 plus 3 times x to the -1 minus 15. In my first row, my common factor is going to be 2 times x to the -1. And then I'll need an x to the -1 here, a -5 here, a 3 here. 3 times -5 really is -15. My not quite a polynomial factors as 2 times x to the -1 plus 3 times x to the -1 minus 5 equals 0. One of my factors has to be 0. Either 2 times x to the -1 is 3, or x to the -1 is 5. Dividing both sides here by 2, x to the -1 is 3/2. So if this were a polynomial, I'd be done now. Instead, I need to get rid of that -1 power. Reciprocal of -1 is just another -1. So I'll have x is 3/2 to the -1, x is 2/3, or x is 5 to the -1, x is 1/5. Negative powers are defined as long as I'm not taking negative powers of 0. Neither one of these numbers is 0, so I don't have any domain concerns. If I really want to check, I can plug in 2 times 2/3 to the power -2 minus 7 times 2/3 to the power -1 minus 15. Throwing all of that unpleasant arithmetic into the calculator, we really do get 0. 2 times 1/5 to the -2 minus 7 times 1/5 to the -1 minus 15, again, really does give us 0. Okay, last one. We have 4x minus 8 times x to the 1/2 plus 3. And the big thing we know is that 1 is 1/2 times 2. And so x is x to the 1/2 squared, at least as long as x is positive. And x to the 1/2 isn't defined if x is negative, so this whole equation fails if x is negative. And so we can actually say that x is x to the 1/2 squared. So what do we have? We have 4 times x to the 1/2 squared minus 8 times x to the 1/2 plus 3 equals 0. And now we're going to pretend this is a polynomial with a variable that happens to be called x to the 1/2. It looks like we're a quadratic trinomial. Our leading coefficient is not 1. So we're going to use the AC method. We have AC is 12, B is negative 8. We need two numbers whose product is positive 12, whose sum is negative 8. I think the numbers we want are negative 6 and negative 2. So we'll have 4 times x to the 1/2 squared minus 6 times x to the 1/2 minus 2 times x to the 1/2 plus 3. First row, my greatest common factor is 2 times x to the 1/2. And then here I'm left with another 2 times x to the 1/2. Here I've got minus 3. Here I've got minus 1. Negative 1 times negative 3 really is 3. My equation in factored form then, 2x to the 1/2 minus 1 times 2x to the 1/2 minus 3 is 0. So either 2x to the 1/2 is 1, or 2x to the 1/2 is 3. X to the 1/2 is 1/2, or x to the 1/2 is 3/2. So either x is 1/2 to the power 2 over 1 is 1/4, or x is 3/2 to the power 2 over 1 is 9/4. Those are my two potential solutions. I started out with an exponent with an even denominator. I have to check for extraneous solutions. And I might as well check for extraneous solutions in my original equation. So I'll have 4 times x minus 8 times x to the 1/2 plus 3. That works out to 0. 4 times x minus 8 times x to the 1/2 plus 3. That also works out to 0. So it really does work out that both of those are solutions to the original equation. Neither one is extraneous, and so I keep both of those solutions.